Welcome to this FMSP online revision session, looking at the Edexcel Further Pure 2 specification. This session is going to look at the topics of inequalities and series. We'll start by looking at the relevant parts of the specification. You need to be able to manipulate and solve algebraic inequalities and inequations, and particularly remembering that you need to be able to cope with the use of the modulus sign. And you need to be able to find the sum of simple finite series, specifically using the method of differences. In this session we will look at the key points that you need to remember for each of these two topics and work through a couple of exam questions. The two topics are completely unrelated, but they're both quite short, so they fit nicely into a single session. We'll start with inequalities. You can multiply an inequality by something which is always negative, as long as you remember to swap the direction of the inequality. But never, ever multiply an inequality by an expression which is sometimes negative. Because if it is only sometimes negative, you don't know whether to change the direction of the inequality sign or not. This is probably the single most important point to remember about this topic, so make sure that you never multiply an inequality by an expression which is sometimes negative. That's what you mustn't do. What about what you need to do? The first step is to rearrange your inequality to have 0 on one side, and then make sure that you've got a single term on the other side, fully factorised, so that you can see what values of x it becomes 0 for. Those values are called the critical values, and you then need to identify the sign of each part of the function between each pair of critical values. Then look at the function as a whole and see whether the inequality is true. Let's look at an example from June 2010. It's always a good idea to read through the whole question first. The first part is just solving an inequality. The second part, though, begins deduce or otherwise. That means that you've got a choice of methods, but that using part A is going to be the easiest way of doing it. Really, when they say deduce or otherwise, or hence or otherwise, they're giving a big hint that using the first part of the question is going to make it easier. And in this question, there's another big hint over here, and that is that the second part of the question is only worth 1 mark. You don't want to be starting again from scratch to solve that inequality. You need to be using what you've done in part A. So let's have a look at solving part A. The first thing you need to do is to get to 0 on one side of the equation. It doesn't particularly matter which side. Sometimes it's easier if you do one or the other, but it's not going to make a huge amount of difference. I do it by subtracting, and remember avoiding having to multiply. Then I want this to be a single term, so I'm going to put it all over x plus 3. So the left-hand bit I've multiplied by x plus 3, and the right-hand bit doesn't need anything doing to it. Multiply out and simplify. X squared plus 7x plus 12, take away 2 is 10 over x plus 3. And then refactorise. So x plus 2, x plus 5, all over x plus 3. My critical values are the values of x which would make that expression 0 or give me 0 on the denominator. So -2, -5 and -3 are my critical values. And now I'm going to look at what happens to the function between pairs of critical values. So here are the components of my function. And across the top, the intervals I'm interested in. So to start with, x being less than the first critical value of -5, then x being between -5 and the next critical value -3, then x between -3 and -2, and finally x beyond -2. Looking at the first part of my function, x plus 5, that is negative if x is less than -5, but once I go higher than that, it will be positive. x plus 3 is negative until I reach minus 3, and then it becomes positive. X plus 2 is negative until I reach minus 2, and then it becomes positive. Looking at the function as a whole, if I've got 3 negative numbers multiplied and divided, then that's an odd number of negative numbers, and the whole will be negative. The second column, I've got 2 negatives, so that will give me a positive answer. The third column, I've got 1 negative, so it will be negative, and the final column is all positive. My inequality needs to be greater than 0, so I'm looking at the 2 parts which are positive, and I can just read my solution from the tops of those columns: minus 5 less than x less than minus 3, or x bigger than minus 2. It's worth just stopping to think how this question would have been different had that been not a strict inequality, but a greater than or equals. My critical values of minus 2 and minus 5 are perfectly acceptable, but my critical value of minus 3 can never be actually used because I've got x plus 3 in the denominator. So although I've got in this second version a non-strict inequality, at the minus 3 x can't be equal to minus 3, so that remains a strict inequality. But for minus 5 and minus 2 I could put in or equal to. So that's just worth noting. The green applies if it was a non-strict inequality. My method for doing this is to always work with strict inequalities, whatever the question says, and then at the end of the question go back and look, okay, I've got equals, when could it actually be equal rather than strictly greater or less than. And now let's have a look at the second part of the equation, of the question. The first thing to note is that if we're looking at the modulus of x plus 3, then the right-hand side of this inequality is always positive. So we know that x plus 4 has to be greater than 0, and therefore that x must be greater than minus 4. So we're not looking at the first column in our table from part A at all. If we look at the second part, where x is between minus 5 and minus 3, well, in our case between minus 4 and minus 3, x plus 3 would be negative, but we've got the modulus of that, so this bit here is going to be positive instead. And that would make the whole function negative at that point. Once we get beyond minus 3, then x plus 3 is positive anyway, and the modulus sign has no effect. So these sections are unchanged. That means that the only section now which is positive is the last section, and therefore my solution to part B is minus 2 less than x. Let's have a look at how the mark scheme is applied for this question. For the first part of the question, just one method mark up to this line here. In other words, getting your inequality with 0 on one side and a single term factorised on the other side. They then give you a mark each, an accuracy mark each, for correctly identifying the critical values of minus 2 and minus 5. And then another mark for using the other critical value to get this inequality here, a method mark and an accuracy mark, and finally an accuracy mark for the final inequality. For part B, it's one mark and they don't care about the method, so it's a B mark, it just has to be right. But note that there is follow through allowed, so that if you've made a mistake in part A and follow through work with correct working, you would still get the mark for part B. That's inequalities. Let's have a look at the method of differences. Well, to start with, I'd like to make a couple of general points which are particularly relevant for this topic. If the question says use a particular method, you must use that method. You will get 0 marks for using a different method. So in particular with questions on the method of differences, if you decide that it would be easier to use standard results from FP1, that might be a perfectly valid method of solving the question, But if the question says you must use the method of differences, you won't get any marks for using standard results. If a question says hence or deduce, you must use your previous answer to continue. And again, if you don't, you won't get any marks, even if your working is valid. If a question says hence or otherwise, or as we had in the last question, deduce or otherwise, you've got a choice. You get credit for using another method, but you are advised to use your previous answer because that's going to be the easiest way to do it. And a couple of points specific to the method of differences. The key here is simply in setting your work out clearly. If you make sure that it's easy to see which terms cancel, you won't have any problems. And just note that you might be expected to find your own partial fractions, which is fine because that's core 4 work, and hopefully you're reasonably secure with that. So let's look at an example. This is June 2010, question 1. The first part is core 4 work. Just find partial fractions. So, big sigh of relief there. Part B, using your answer to part A, you must use those partial fractions you found. And the method of differences, you must use this method. And then just watch part C. That limit there. Take care. And give your answer to 3 significant figures. Okay, let's do the partial fractions. So this is a nice, standard, straightforward example. And the usual format is A over the first factor plus B over the second factor. And then we recombine them. So that's A multiplied by 3r plus 2 plus B over 3r minus 1 all over 3r minus 1. 3r plus 2. And note that I've used 3 lines. I've said identically equal to, so these expressions are true for all values of r. And if we look at the first and last of the 3, we note that A times 3r plus 2 plus B times 3r minus 1 must be equal to 3. Note that this is true for all values of r, including those values of r for which the denominator is undefined. Well, the denominator is 0, meaning that the whole expression is undefined. We can't say that r is equal to a third, but we can use it in order to find a and b. If r is a third, the bracket for b is 0, and we just get 3/3, which is 1 plus 2 is 3. A is 3, and therefore A is 1. And if r is minus 2/3, the bracket for A disappears, and I get minus 3b equals 3, and therefore B is minus 1. So this identity here was true for all values of r, including the ones where the whole expression is undefined. And using that gives me an easy method of finding A and B. So, finishing this off, I write 3 over 3r minus 1, 3r plus 2 is identically equal to 1 over 3r minus 1, take away 1 over 3r plus 2. Fortunately, I've got a minus sign there because I need to use the method of differences. If you do a question like this and find you haven't got a minus sign there, then you know you've made a mistake, and hopefully you'll be able to go back and find it. So part B, using my answer to part A. So I've got the sum from r equals 1 to n of 3 over 3r minus 1, 3r plus 2. And I've just shown that that is equal to the sum from r equals 1 to n of 1 over 3r minus 1 minus 1 over 3r plus 2. I'm using the method of differences, so I'm just going to start writing out terms. If r is 1, then 3r minus 1 is 2, so that gives me a half. And 3r plus 2 is 5, so take away a fifth. If r is 2, 3r minus 1 is 5, so plus 1/5, and minus 1/8. If r is 3, 3r minus 1 is 8, so that's plus 1/8. 3r plus 2 is 11, so minus 1/11, and so on. Looking at the end of my sum, I'm going to take the case where r is n minus 1. So 3 lots of n minus 1 is 3n minus 3. Take off another one, that's 3n minus 4. Take away 3n minus 3 plus 2 is 3n minus 1. And the final term when r is n is just 1 over 3n minus 1. Take away 1 over 3n plus 2. And you can see that everything inside these big square brackets cancels out, and I'm just left with a half minus 1 over 3n plus 2. Need to put that as a single fraction, so over a denominator of 2 lots of 3n plus 2. I've multiplied the 2 by 3n plus 2, and I've multiplied the 1 by 2, and that gives me 3n over 2 lots of 3n plus 2 as required. And the final part, this is equal to the sum from r equals 1 to 1,000. 3 over 3r minus 1, 3r plus 2. Take away. Now this is where it's very easy to go wrong. I need 100 in the bit I've got left, so I don't want to be taking that off. So the bit I'm taking off is only r equals 1 to 99. Let's just put the formula from the previous page up so that you can see what that was. 3n over 2 lots of 3n plus 2. So the sum from 1 to 1,000, n is 1,000, so that's 3,000 over 2 lots of 3,002. Take away 3 lots of 99 is 297 over 2 lots of 297 plus 2, which is 299. Putting those into a calculator gives me an answer of 0.00301 to 3 significant figures, which you may remember was required in the original question. It's up there, isn't it? 3 significant figures. I underlined it when we looked at it on the first page. So let's have a look and see how the mark scheme works for this question. In part A, it's simply one method mark and one accuracy mark. So if you do some fairly reasonable working, you'll get the method mark, and if you get the correct answer, you'll get the accuracy mark. For part B, there is a method mark for clearly using the method of differences and an accuracy mark for doing it correctly, and there's follow through. So if you got your partial fractions wrong, then there is follow through at this point. And for the last bit is just one accuracy mark and no errors. So you've got to get to the given result without any incorrect working to get that final accuracy mark. And for the last part, there is a method mark for noting that the second sum is to 99 and attempting to substitute. And a final accuracy mark for getting the right answer. Well, that is inequalities and series. I'd like to wish you all the best with your revision for this exam and look forward to your company in another online video for this specification.